Welcome to Propeller Breeze, the show for student pilots, sim fans, and everyone chasing that first solo and beyond. All information in this podcast is for entertainment and general knowledge only. Always verify with certified flight instructors or regulatory authorities before attempting anything mentioned here.
Learning to fly, especially when you're working towards that private pilot license, it's an incredible journey. But let's be honest, right? There are times when figuring out how your plane actually moves through the air can feel a little, well, maybe a bit like magic, all those invisible forces. The way the propeller just seems to pull you forward. It's a lot to wrap your head around, particularly when you're just starting out as a student pilot. So today, we're going to cut through some of that mystery. We're doing a deep dive into two really critical areas for every aspiring pilot. First, how that propeller up front actually works to generate thrust, and then those sometimes, let's face it, frustrating left-turning tendencies that seem to challenge every single takeoff and climb. Our mission today, to unpack your sources, pull out the essential insights, maybe some surprising facts, and give you that practical understanding you need to feel, confident and really well-informed about these fundamental forces.
Yeah, and this isn't just about passing the written exam, is it? I mean, knowing this stuff is absolutely fundamental. It helps you anticipate what the aircraft's going to do. And that lets you make precise, timely control inputs, especially during really critical phases like take off that transition from ground to air in your initial climb out. Knowing why the plane wants to turn left or why the prop works the way it does helps you stay ahead of the aircraft, makes you safer, more confident.
Definitely. Okay, so let's start with the propeller. Let's demystify that.
Yeah.
For a lot of us, it's just this spinning blur at the front, pulling us along. But what's maybe the most surprising or counterintuitive thing a student pilot should grasp about how that fan actually creates thrust? Because it's so much more than just a fan, right? It's this precisely engineered thing, two or more blades, a central hub. But here's what really got me when I first learned it. Each of those blades is essentially a rotating wing.
That's exactly the way to think about it. A perfect analogy. If you could take a slice through a propeller blade, look at its cross-section, you'd see an airfoil shape, just like your plane's wing. One side is cambered, curved like the top of a wing, and the other side is relatively flat. And the chord line, it's just an imaginary straight line from the very front edge, the leading edge, back to the trailing edge.
Okay, and we hear terms like blade, angle, and pitch thrown around. What's the difference there?
Blade angle, that's the angle between the blade's chord line and its plane of rotation, right? Measured in degrees. But pitch? Sometimes people use them interchangeably, but pitch is more about the distance it would theoretically screw through the air in one turn, assuming no slip, like inches, maybe?
Exactly. You might see a prop described as, say, 74/48. That's 74 inches long, with an effective pitch of 48 inches per revolution. It's basically describing how big a bite of air the propeller takes with each rotation.
Got it. So that bite is how it generates thrust. That's a big part of it, yeah. Just like a wing generates lift, the airfoil shape of the blade creates a pressure difference. You get lower pressure in front of the prop, higher pressure behind it. That pressure difference effectively pulls the aircraft forward. But thrust also comes from the angle the propeller blade meets the air, its angle of attack, or AOA. It deflects air backward, creating dynamic pressure behind the blade. Basically, you could think of thrust as the propeller grabbing a mass of air and accelerating it backward. It's a mass of air handled times the slipstream speed minus the aircraft speed. More air, faster backward, equals more thrust.
And how well does it do that? That's propeller efficiency.
Right. That's the ratio of the useful power you get out, thrust horsepower, compared to the power the engine puts in, brake horsepower. It varies, maybe 50% up to around 87% in good conditions. Depends partly on propeller slip.
Ah, slip. That's the difference between the theoretical distance it should travel forward and how far it actually travels. Because air isn't solid, Mark.
Precisely. Air slips past the blades. Geometric pitch is the ideal. Effective pitch is the reality. But here's something really crucial for efficiency, especially for pilots to understand. The propeller twist.
The twist? Why is it twisted?
Well, think about it. The tips of the propeller blades are traveling way faster than the parts near the hub, right? They cover a much bigger circle in the same amount of time. If the blade had the same angle all the way along, no twist, the inner parts near the hub might actually be at a negative angle of attack, creating drag. And the tips, they could stall at cruising speeds because their angle of attack would be too high.
So without the twist, the prop would be really inefficient, kind of fighting itself.
Exactly. The twist ensures that pretty much the entire length of the blade is working at a reasonably constant and efficient angle of attack, especially in cruise. It helps equalize the thrust produced along the blade. It's clever engineering to make sure the whole blade contributes effectively.
Okay, so that angle of attack, the AOA, what's the sweet spot? For efficiency, you want it pretty small, right? Just enough bite without too much drag, like +2 degrees to +4 degrees.
That's the ideal range for peak efficiency, best lift-to-drag ratio on that little airfoil blade. But with a fixed-pitch propeller, the kind you find on many trainers, the actual AOA in flight changes quite a bit. As your airspeed changes, that relative winds hits the blade differently. So the AOA might vary, maybe from 0 degrees up to 15 degrees or so. And you, the pilot, can't change it.
Which leads us nicely into the two main types of props you'll encounter.
Right. Fixed pitch and constant speed. How they manage that AOA is key.
Okay, so fixed pitch first. Like you said, common on trainer. The angle is set, fixed. They're designed for peak efficiency at one specific speed, usually cruise speed.
Generally, yeah. It's
Yeah.
a compromise.
So outside that sweet spot, efficiency drops off, like
Yeah.
on takeoff.
Absolutely.
Yeah.
When you're sitting still or just starting your takeoff roll, engine RPM might be high, but your forward speed is low. The fixed blades are at a really high angle of attack then, very inefficient. Lots of drag, not much thrust for the power being used. That's why takeoff roll feels sluggish initially.
Right, you feel that waiting for speed to build. Okay, so contrast that with constant speed propellers.
Now this is where things get more sophisticated and much more efficient across the board. These props automatically adjust the blade angle, the pitch, to maintain the most efficient AOA for whatever you're doing. Takeoff, climb, cruise.
So they're always trying to find that optimal +2 degrees to +4 degrees AOA we talked about.
Pretty much, yes. The system works to keep the engine RPM constant, which indirectly optimizes the AOA for efficiency.
Okay, so how does that work in practice? Takeoff, for instance, you need maximum thrust.
Right. For takeoff, the constant speed system automatically sets a low blade angle, a fine pitch. This allows the engine to spin up to its maximum rated RPM, producing maximum power. Even though each blade rotation takes a smaller bite of air, the high RPM means it's taking many bites per second. That high RPM and the resulting high slipstream velocity, combined with your low forward speed, gives you maximum thrust to get off the ground.
And then after liftoff, as you climb and accelerate.
As your airspeed increases, the system automatically increases the blade angle to a higher pitch, a coarser pitch. This keeps the AOA efficient, preventing the engine from overspeeding. It takes a bigger bite of air with each revolution now. This allows you to reduce the engine RPM slightly for climb or cruise, which saves fuel, reduces engine wear, but still maintains optimal thrust for the phase of flight. It's constantly adapting.
And you, the pilot, manage this with the prop control, usually the blue lever.
Exactly. You're managing the power setting. After a takeoff, to set climb power, you typically reduce manifold pressure first with the throttle, the black lever. Then you increase the blade angle using the prop control blue lever to bring the RPM down to your desired climb setting.
Same for cruise. Reduce manifold pressure, then increase blade angle further to lower RPM for economy.
That's the standard procedure, yes. You're matching the propeller's load to the engine's power output for efficiency. Always reduce manifold pressure before reducing RPM.
Okay, so that prop is doing amazing work pulling us forward. But it also creates some unintended side effects, right? That's where these left-turning tendencies come in. Every student pilot feels this, that tendency for the plane to want to yaw or roll left. Let's dig into the why. What are these forces?
Yeah, this is crucial stuff for smooth, precise flying. There are four main culprits we talk about: torque reaction, the corkscrewing slipstream, gyroscopic action, and P factor, or asymmetric loading. And the key thing to remember is they don't always act equally. They interact. Their strength changes depending on what you're doing: takeoff, climb, slow flight, and your aircraft type.
So it's not just one thing pushing left, it's a mix.
It's a dynamic mix.
Yeah.
Your job as the pilot isn't just to stomp on the right rudder, but to feel the combination of forces and apply the right correction. It's more like a dance.
Okay, let's break them down. First one, torque reaction. Sounds like physics class.
It is. Newton's third law. For every action, there's an equal and opposite reaction. Your engine and prop are spinning clockwise, as seen from the cockpit in most U.S. planes.
Right.
So there's an equal force trying to rotate the entire aircraft the opposite way, counterclockwise, which means rolling it to the left.
Ah, so it's a rolling tendency primarily.
Airborne. Yes, it acts around the longitudinal axis, wanting to roll you left. Aircraft designers try to compensate, maybe offsetting the engine slightly or rigging one wing for a bit more lift. Aileron trim helps too.
But what about on the ground during takeoff?
On the ground, it gets a bit more complicated. That same rotational force pushes the left side of the aircraft down harder onto the landing gear. More weight on the left main wheel means more friction, more drag on that side.
Which tries to yaw the aircraft left around the vertical axis.
Exactly. So on takeoff, torque gives you both a left roll tendency and a left yaw tendency due to that extra drag on the left wheel. How strong it is depends on engine power, prop size, aircraft weight, even the runway surface.
Okay, so compensation for torque is mainly right rudder on takeoff, maybe some right aileron, airborne, or trim.
That's the basic idea, yes. Anticipate it, especially when you apply full power.
Got it. Next, corkscrewing effect of the slipstream. You said imagine a corkscrew.
Yeah, visualize the air coming off that spinning propeller. It doesn't flow straight back, it spirals like a corkscrew. Now, this spiraling slipstream flows back and hits the left side of your vertical tail fin.
Pushing the tail to the right.
Right. Pushing the tail right, yaws the nose to the left.
When is this effect strongest?
It's most noticeable when you have high power settings and low forward airspeed. Think takeoff, or maybe practicing slow flight or power on stalls. The spiral is tighter, more compact, hits the tail harder. As you speed up in cruise, the spiral stretches out, becomes less effective, has less impact on the tail.
Interesting. Your source mentions something curious, though. This corkscrew can also cause a slight right rolling moment. How does that work?
Yeah, that's a finer point. As that spiraling air flows around the fuselage, the upward flowing part on the right side might slightly increase the effective lift on the right wing, while the downward flow on the left decreases lift there, causing a slight right roll.
So it might counteract the left roll from torque a bit.
It might, but remember, these forces are constantly changing balance. Torque roll is usually more dominant. Your main job is just to correct whatever the net result is. Don't overthink the components in the moment, just fly the plane.
Okay, good advice. Third element, gyroscopic action. The propeller as a gyroscope.
Exactly. Any spinning mass exhibits gyroscopic properties. For pilots, the most relevant one is precession.
Precession.
No.
Remind me, if you push on a spinning gyroscope.
The force doesn't act where you push it. It acts 90 degrees ahead in the direction of rotation.
Okay, 90 degrees ahead. How does that apply to my airplane propeller?
Think about a tailwheel aircraft during takeoff. As you push the stick forward to raise the tail,
Right. The nose pitches down, tail comes up.
you're effectively applying a force to the top of the spinning propeller disc, pushing it forward. Precession means the resulting force acts 90 degrees clockwise from the top. Which point is that?
The right side of the prop disc.
Exactly. A force pushing forward on the right side of the prop disc yaws the nose.
To the left.
Bingo. So raising the tail in a tail dragger induces a left yaw due to gyroscopic precession. It can also cause pitching moments if you make sharp yaw inputs, like maybe during aerobatics, but the tail-raising example is the classic one for PPL students.
So again, be ready with the rudder, especially in a tailwheel plane when lifting the tail.
You got it. Use elevator and rudder smoothly to counteract unwanted pitching or yawing.
All right, last one, asymmetric loading or P factor. This one always felt the most complex.
It can seem that way, but it's crucial, especially during climbs. It happens when the aircraft is flying at a high angle of attack.
Like right after takeoff, climbing out.
Perfect example. At a high AOA, the propeller disc isn't meeting the oncoming air straight on. It's tilted relative to the airflow. Now think about the propeller blades. One side is moving downwards, the right side from the pilot seat, and the other side is moving upwards, the left side.
Okay.
Because the aircraft is pitched up, the downward moving blade on the right meets the relative wind at a higher angle of attack than the upward moving blade on the left. It takes a bigger bite of the air.
Higher AOA means more lift, or in this case, more thrust.
Exactly. The right side of the propeller, the downgoing blade, generates more thrust than the left side, the upgoing blade.
So the thrust isn't symmetrical anymore.
Correct. The center of thrust effectively shifts to the right side of the propeller disc.
And if the main thrust force is acting on the right side of the center line...
It creates a yawing moment to the left. That's P factor.
Okay, that visualization helps. More thrust on the right yaws the nose left, and it's strongest at high angles of attack.
Yes. High power settings combined with high angles of attack. That's why you need significant right rudder during a steep climb, especially right after takeoff. As you lower the nose and decrease the AOA for cruise, P factor diminishes significantly.
Wow. Okay, so putting it all together. Torque, slipstream, gyro, P factor. Quite a cocktail of left-turning forces.
It really is.
Yeah.
And like we said, their relative strength changes constantly. P factor and slipstream are strong on takeoff and climb. Torque is always there when power is applied. Gyroscopic effects are most noticeable during pitch changes, especially in tailwheel aircraft.
So the big takeaway for you, the student pilot listening, is what?
It's that you need to anticipate these forces. Understand when they'll be strongest. Feel what the airplane is doing. And then apply smooth, coordinated control. Inputs rudder, primarily for yaw, but also aileron and elevator as needed to counteract those tendencies and maintain positive control.
It's not about fighting the airplane, but guiding it. That constant dance, like you said, that rudder tap dance on takeoff is real.
It absolutely is. Every pilot does it. It becomes intuitive over time, but understanding the why behind it accelerates that learning process immensely. It turns you from someone just reacting into someone who is actively piloting.
So you've just taken this deep dive with us into the invisible forces shaping your flight. Really understanding how your propeller works and why your plane wants to turn lift isn't just, academic knowledge for the test. It's about building that intuition, that feel for the airplane, that precision. That's what really separates someone just operating the controls from a true pilot.
Absolutely. So here's something to think about on your next flight, maybe your next lesson. How will actively anticipating these specific forces, feeling for the torque on power application, predicting the P factor in the climb, compensating for the slipstream, how will that change your experience? How will it make your next takeoff and climb feel more confident, more controlled, more like you're truly in command?
That's it for this episode. Keep your wings level, your brain sharp, and catch you next time in the pattern. Thanks for riding with Propeller Breeze.